So if I look at gamma of 1/2, now with the translation here, okay, so for the gamma of 1/2, so if I let x be equal to 1/2, so I'm looking at going from 0 to infinity, and I have t to the 1/2 minus 1, so this will be t to the negative 1/2 times e to the negative t dt. Now, if I look at integrating, and we'll just take what we have here now for the general integral. So if I have the integral of t to the negative 1/2 times e to the negative t dt, and creating a pathway through u substitution. Let's say that if I have that u is equal to t to the 1/2, and I squared the relationship. Okay, so u goes to u squared, and I have is equal to t. And if I take the differential on both sides, left-hand side, we have transforming from u squared to 2u du, and to the right, okay, I have is equal to dt. And some things we have going on simultaneously. Okay, so I have u is equal to t to the 1/2. Okay, and since I'm working with t to the negative 1/2 as opposed to t to the 1/2, I'm going to have that u to the negative 1, or the multiplicative inverse of u, is equal to t to the negative 1/2. And utilizing what we have here, so I have the integral for t to the negative 1/2. We have u to the negative 1, and I have times e to the negative t. So this would be e to the negative u squared. And just do a little bit of color coding here. And for dt, I have 2u du. And as for what we have in the substitution variable u, we have the multiplicative inverse of u times u. Say those will cancel each other out. And in following through, now I have the integral of 2 times e to the negative u squared du. Okay, and so if we take what we have here back into the improper integral, so we're looking at going from, again, from 0 to infinity, and again in place of t to the negative 1/2 times e to the negative t dt, again I have what is going to be 2 times the integral as t goes from 0 to infinity, or in this case as u goes from 0 to infinity, of e to the minus u squared du. And guess what? Regardless of the variable, you have e to the square of, or I should say e to the negative of the square of the variable in the differential of the same variable. Okay, as the variable goes from 0 to infinity, we have the square root of pi over 2. And here I have 2 times the square root of pi all over 2. So we have with gamma of 1/2, okay, this will come out to the square root of pi. Okay, and so just utilizing what we have here, And we have at the foundation, having just taken the result of gamma of 1/2. Again, gamma of 1/2 is equal to the square root of pi. And if I were to project on out, say if I have adding 1 to 1/2, I have gamma of 3/2, which would be gamma of 1/2 plus 1. And so you have x would be at 1/2. So I'm looking at 1/2 of the gamma of 1/2. Gamma of 1/2 is equal to the square root of pi. So this would be the square root of pi all over 2. And if I were to go out to gamma of 5/2, so this would be gamma of 3/2 plus 1. This time your x value, again, is going to be 3/2. So looking at 3/2 times the gamma of 3/2. So we're going to have 3/2 times what's going to be the square root of pi over 2. So this will be equal to 3/4 of the square root of pi. Now we'll just take one more. So we have a gamma of 7/2. So we're looking at gamma of 5/2 plus 1. Then we have 5/2 of the gamma of 5/2. This time we're going to have 5/2 times 3/4 of the square root of pi. So for gamma of 7/2, okay, so we're going to have 15/8 of the square root of pi. And if I were to continue throughout, okay, I would have like gamma of 9/2, that would be like 7/2 times 15/8 to the square root of pi. So there's a bit of a domino effect that will be carried out. And this will be for some of our functions relayed to what we'll be looking at in the case of Laplace transforms.